Business group. We're gonna do class stuff. Grab your homework 3.1. I think we started talking about this yesterday, the different types of forces. What?
Yeah.
No.
Why?
Because.
Why?
Because class started 5 minutes ago.
Well, I forgot. I don't.
Okay. Do your best. Maybe you could grab a piece of paper up here.
Can I go with it?
No, stay here.
Can I go to the bathroom?
No. No, Travis. Come to class prepared.
You gotta get close to the camera and say that.
So yesterday when we were talking about forces, we talked about the different types, correct? And how
Yeah.
we note each. Okay. So we talked about friction and normal force and weight
Yeah.
and tension. Good. So let's start then. We're going to do 3 problems together so you can see the method and what we're doing in each of these. Problem 1 here has 2 books. One book sitting on top of another, both of them sitting on a table. We're going to draw out the forces on each of these. But part of this, for free body diagrams, we have to treat each object separately. So any object that could potentially move differently. So we're going to have 2 books drawn out when we're looking at this, book 1 and book 2.
So this be going in squares.
Yeah, this goes in the squares on the worksheet. Give yourself some room around it to write. If you are not writing in the worksheet, you can use as much space as you want.
Got it. I mean, I would have that worksheet. Well,
But you opted not to come to class prepared. I get you. I hear you.
I didn't have time. I was trying to make that time. He's catching them good.
Now we want to, on each of these, let's just start with book 1. We want to write down, sketch an arrow for every force that's acting on it, and then also label it so that we know what each of those forces is. So book 1, this is the bottom book. Let's do book 2, it's even easier. Book 2, what forces are acting on book 2?
Is it like just like laying like on a table?
Yep, there's a picture here. And there are just 2 books, one laying on top of the other on a table. Book 2 is on top.
So then one going this way,
What is one what?
down.
One
Yeah.
force.
A force.
What kind of force?
Okay.
Static.
Gravity. Gravity goes down. You can label that either way. You can do a FG, or I prefer to just write it out. It saves us a step later. MG. But now, because we have 2 objects, we have to be really careful of how we're labeling things. So I put an FG2 or for force of gravity on book 2. Or if I'm using the MG, I'd label that M2 times G for the actual value of the weight. Okay, what other forces are acting on book 2?
Normal.
Normal, why?
Because it's sitting on that table.
It's not sitting on the table though.
Sitting on other books.
Sitting on the other book. So the other book must be pushing up on it. Yep. Anytime you've got 2 surfaces together, you'll have a normal force, so an Fn. Now we could potentially have lots of normal forces depending on how many things are touching. So we have to be careful about labeling them too. The way that I usually use is to add a couple characters after, numbers or letters or whatever. So I'm going to say this is a normal force on book 2 from book 1. So that'd be a 2-1. Now it doesn't have any ropes, so there's no tensions. It's not sliding, or because it's flat, it's not even potentially sliding, so there's no frictions. Yeah.
Won't that Fn arrow be going down?
What direction is book 1 acting on book 2?
But the way you wrote it, isn't it the book 2 acting on book 1 with the 21?
We are always looking at just the forces acting on the object, not the other way around.
Okay.
So book 1, so gravity is pulling our book down.
Yeah.
But book 1 on the bottom is pushing up onto book 2.
Okay.
But we're not, and we won't ever here look at, when we're considering book 1, we don't consider what it's doing to other things, only what's happening to it. But that brings us to book 2. That's all the forces acting on it. That brings us to book 1. What forces are acting on book 1?
Right.
Gravity again, from the center straight down, and that would be an FG1 or M1G. Okay, what else?
Normal.
Book 2 is, right? So where and in what direction is book 2 acting on it? Down from the top, right? Sitting up on top. And so this, what kind of force?
Normal.
Normal force. So an Fn acting on book 1 from book 2.
Is there a normal force?
Up from the table as well, right? That's what's keeping it from sinking down. So we'd have a normal force acting on book 1 from the table. To simplify the next couple steps, we should also apply one of Newton's laws here. Newton's third law, equal and opposite forces. Whenever you've got two things interacting, we can look for these to help us simplify later. Anything here that should be equal and opposite forces? Yeah, Kate.
Would it be the FN12 and the FN21?
You got it, because those are, and that's why, so one's pushing down, but the other's pushing up with the same force. So these two are equal. Okay, so once you've identified and sketched out all of the forces, you will typically draw sum of the forces equation. So this is adding up all of the forces so that we can see what happens. This is applying Newton's second law, which is the math one. So we're going to do a sum of the forces. We're going to do it in the y dimension, and to begin with, we have to do it separately, so we're only going to do book 1. Oh, I forgot one step up here. One other thing we have to label here is the direction, if any, of acceleration. None. Not in this case. They're sitting on the table, they're not going to suddenly move, so let's make a note of that. If this was something that you were lifting both of them, you would have acceleration pointing up, most likely. If you were lowering it, you could have acceleration pointing down. That direction is the positive direction when we start writing formulas. But in this case, with a equals 0, we don't have one defined, so we'd probably just go back to the normal that up is positive, down is negative. It ultimately wouldn't matter as long as you are consistent.
What's that symbol mean again?
Somehow.
Sum of, yep, and so sum, S-U-M.
Okay.
Sigma is a Greek letter S. And whenever you see it, it'll be a sum. So this is the sum of the forces acting on book 1 just in the y direction, which is the only one we care about. Anything acting in the positive direction is positive. So that would be the Fn1t, the normal force on book 1 from the table. Anything acting in the negative direction down is negative. So we'd subtract off the weight, M1g, and we'd subtract off the normal force from book 2. The last part of this is from Newton's second law. Not just in this case, but in any case, if we add up all the forces on something, what is it equal to?
It's gone.
I can easily.
Nothing.
Average.
No, look at Newton's second law. You wrote it down yesterday.
M-A.
M times A, the object's mass times its acceleration. So its mass is M1, its acceleration is A, but in this case we are already discussed that A is 0. I want you to write that each time though, because it won't always be 0. It may not even often be 0. So don't forget that it is there, even though in this case it's 0. And what it says is the upward force must then be equal to the downward forces because they add up to 0. So it's balanced, it's not moving anywhere. Let's do the second one. Fy for book 2, same deal. We had one upward force, which was the normal force on book 2 from book 1, minus the gravitational force M2G is equal to, just like before, M2 times A. So it's mass times acceleration, which again is 0 in this case.
Would make that whole thing 0 then?
This is 0, yeah. So what does that tell us about these two? They're the same, just opposite directions. So if we also realize that these two are the same, because they're the equal and opposite forces between the books. So if we took this one, F2 N21 must equal M2G, we could also put it up here. And so just to rewrite our first equation, but now with this substitution, the normal force between the book 1 and the table must be equal to M1G, minus M1G, minus that value, M2G. We know that's equal to 0. Well, what does that mean? Well, it means that the normal force between the table and the book must be equal to both M1G plus M2G. So the amount of force that the table has to push up with has to be equal to the weight of the two books on it. Pretty simple thought, but this is kind of the proof of it, and we are going to expand that a lot as we go through. Any questions on those? Okay, let's go on to the next one, which is mass, just a block, is held up by a string. There's only one mass here, so it's an old, relatively poor physics joke that various punchlines are that the string is massless. It's just a physics thing. We don't usually consider the string in a problem like this as a separate object. It's just there to supply some force, and we're not going to change from that. So when we have strings, we're just going to say, okay, they connect these two things, but we're not going to worry about them. So instead, we just have a mass here. And it's being held up by a string. We just aren't going to write it. We're just writing the block. What forces are acting here? Gravity, mass. Yeah. We don't have to, there's only one object, so we can just label it mg. What else? Tension. What direction?
Wait, is it getting held like this?
Yep.
Is it held like this?
No, it's held like this by a robot.
Tension would be up.
Tension would be up, right. Tension like so. What about the acceleration on this? 0, we're just holding it. So again, we kind of default to up being positive. And then we go and we write our sum of the forces. Up, we have a tension. Down, minus down, we have mg. What's that equal to?
MA.
MA. Good take. Most people just say 0, which it is, but write MAF. So that term is 0, which means that the tension must be equal to M times G. Another easy peasy one. But they're really just to show you the methods.
Yeah. You're just like Miss Keys.
Yeah?
Gives you a couple ones like 2 plus 2 equals 4, and then she throws some random stuff on you.
Well, I'm going to do another one that's tougher. Unless you keep complaining.
It'd be nice to have a homework.
It would be nice. I agree. You should totally do that in the future. Let's flip to the next page. So the next 2 pages are sort of the homework part, but I want to do one of those with you as well. The first part of this, 3 through 7, has setups just like, well, the setups aren't the same, but what I'm asking you to do is the same as what we've done here. Label the forces on any of the objects, and then write the sum of the forces equations. The page after that, then, put some actual numbers into it, so the flip side of that second page. And you'll actually do the full calculation.
This is all.
But see, I'm building you up to it.
This is all one assignment?
Yeah.
Is this that one that's like 3 pages?
Well,
Why was some such long assignment?
it's 11 problems.
Exactly. I'm used to like.
And
5.
it's 11 problems, and I'm doing 3 of them. So it's really 8 problems.
Don't complain, it'll make us do more.
Okay, let's look at number 4. Number 4 has 2 boxes being pushed across the floor.
What?
Got a force here, which we'll call an F push. Now we're actually going to split this up, but this is what and it's got an acceleration this way. Just in case you forgot your homework,
Oh, thanks.
then this is what it looks like.
Oh, I remember.
So we want to split this up so we're looking at the 2 objects separately, and then write equations for each of the objects. So let's look at box 1 first. What are the forces?
I thought you were doing that.
And since there are multiple things now, I'm going to be careful to label it M1 times G. What else? Somebody else. Let's go to
Is there something, is it friction this way?
No, it has a little hand printed on there, right?
Yeah.
It's a push. We can just label it as a push or an F push. That way. Kevin, what's another one?
Normal.
Normal, where?
The table to the box.
Table to the box. So what direction?
Up.
Up, you bet. The table is pushing up on the box. I'd label it Fn on box 1 from the table. Tate.
So I know we kind of already stated this, but would your acceleration be 0? It's just sitting there.
Nope, it isn't just sitting there. It actually specifically says on the worksheet.
Oh, I
There's
remember
an
that. now.
acceleration. And so, but that's not a force regardless.
Okay. There'd be. Okay, so you said it's getting pushed. So would that be kinetic from box 2 to box 1?
No,
No.
it's not friction between the 2 because when do you have friction?
When 2 things are moving together.
When they're sliding against each other, you do.
Okay.
But this is just one thing pushed.
So is it just a normal? then?
It's a normal force.
Okay.
So there's a normal force on box 1 from box 2. What direction?
That.
Yep.
Yeah, that way.
I saw several correct fingers that way. But box 2 is resisting the push, so it's pushing back. Normal force on box 1 from box 2. There's one more force, Travis.
Friction against the table.
Friction against the table. What direction?
That way.
That way, yeah, right. Always opposite the direction of motion. We know the direction of acceleration, and since that's where the push is going, that's probably the direction of motion as well. So friction would be back here, and it's what kind of friction? I think you might have said already. Kinetic, because it's moving. FK. And we'll put it FK1, just to label it. That is a lot of forces. It's pretty simple, but it's a lot of forces. Yeah, pretty simple situation. Let's look at box 2, which is next to and being pushed by box 1. Haley, what's a force? Gravity. M2G going straight down.
She seems to know.
Travis,
Why?
what's another force?
Box 1 pushing on box 2.
What kind of force would that be?
Push. Normal.
Normal force. 2 surfaces, normal force. F normal on box 2 from box 1. What's another one, Tate?
Hold on, man. I'm writing that one down. So yeah, so you have the friction from the table.
Friction from the table. What direction would that be?
That way.
That way. Same way as before, because they're both sliding this way. So we'll do a kinetic friction too. That's it. Oh, wait, sorry, there's one more.
Push.
No.
Normal from the table.
So if you find one key, pretty much just copied over the next.
Not always, because you do notice there's no F push on this box.
True.
We're not pushing on that box. We're pushing on box 1. Box 1 is then pushing on box 2. So, but that is, in this case, the only difference. Okay, so now we've got to do some of the forces equations. And in the worksheet, I've got 4 squares for this. One for X for each box, one for Y for each box. Let's do Y first because it's easy. We know it's moving in X, so that means Y is going to probably be easier. So some of the forces on box 1 in the Y. Only 2 things are going.
FNIT,
Yeah.
or FN1T.
Yep. And that's, since there's no acceleration in the Y, we'll just call up positive. We'll subtract anything negative, M1G. Tate, what's that equal to?
MN.
M1A for this.
Well, yeah,
right,
M1A.
And what's that equal to here?
0.
0. And I'll put a little AY, because we could still have an acceleration in the X, and in fact we do. Okay, let's do the sum of the forces on box 2. Same thing, except that we put 2's in. Fn2t minus m2g equal to m2a. And that in the y. And that is also 0. And all that's saying is that it's not accelerating in the y at all, so the floor just has to push up with the same amount of force that gravity is pulling down. X is more, it's the same method, but it's more interesting in this problem.
The F push is positive.
F push is positive because it's in the same direction as the acceleration. These 2 are negative. And normal between 1 and 2. Tate, what's that equal to?
MA. And the X.
In the X, good. Which is not 0 here. So we can't cross that out.
Wait, why?
Well, it's told that we're told that we have an acceleration.
Oh, okay.
We don't know what it is yet.
Why is F and 12 negative?
Because it's pushing in the opposite direction of acceleration. Acceleration tells us the positive direction. Okay, let's do some of the forces in X. Oops, that should have been a 1 on box 2.
So you're positive is that FN21.
Yep, same direction. Then we only have 1 negative, which is friction. FK2. Tate, what's that equal to?
MAX. M2AX.
Good. So let's inspect this a little bit and see what we can see, especially with Newton's third law, the equal and opposite forces. Are there any?
Yeah, 12 and 21.
Yeah, these 2 have to be equal. That can help us simplify stuff in the X, because if we wanted to, we could say, oh, well, if I could solve for this and put it in there. That's an algebra thing. We're not going to, on the front page, we're not doing the algebra part. We're just writing
On the
these.
back page, we are not.
But on the back page you are. So that's an important note because those 2 mean the same thing. You could even rewrite this as Fn1, 2 if you want. Any other equal but and opposite forces? Look at those formulas we wrote. Anything else that's got to be equal?
The friction not coming off the table equal.
No, because those are bad together, right?
So these, we don't know the exact relationship, but we do know that F push must be greater because there's an acceleration. So it must be greater than these 2, and Fn21 must be greater than friction here because we've got an acceleration.
FK2 would equal F push minus.
Yeah, so those are, if we take a bunch of them, they're equal together. Or actually, they're not equal. They're, because we've got a term here, they're not equal to 0. But look up here. If these 2 are equal to 0, then these 2 must be equal but opposite forces. That makes sense. They're technically not, but they are equal to each other. They're not Newton's third law type. And these 2 are equal because of how this works out. That's really helpful when we get into the math usage of it. But here it's just something to note that since it's not accelerating in the y direction, the forces up must be equal to the forces down. We don't know enough information yet to talk much about the frictions. They could well be different depending on each box. And yeah, what about the accelerations, AX1 and AX2?
Aren't those the same as the afterpush?
No, they are not this.
No, wouldn't they be the same as the friction?
No,
Come from the table?
nope. They are accelerating, so we know that that the force being applied to your right is greater than any forces being applied to the left. That's why it's accelerating. The point I want to highlight, which is maybe too obvious to even say, these two have to be the same, because those two boxes are moving together. You can't have a greater acceleration on one than the other. So those two are the same, which is why I didn't even think to label them. They're moving together. That actually brings me to the discussion of, which I can, yeah, it'd be good to discuss now, because that wasn't on the last video. The discussion of Newton's third law with equal and opposite forces, which we talked about yesterday, but not a ton, and I want to talk a little bit more about that. Then you'll have some time to work on these. The equal but opposite forces. Let's take the example from first. The book 1 was pulled down by Earth. By the Earth, pulled down by the Earth. And let's just say that it was 10 newtons of force, just to put a number up in there. We know that every force has an equal and opposite force, or at least that's claimed by Newton's third law. Since it's reached the status of law, we can be pretty confident in it. What's the equal and opposite force of that then? What would be?
Normal?
That's a very common misconception, but let's take a look at a book here. It's being pulled down by gravity with, let's say, 10 newtons of force, pulled down by the Earth. My hand is not the thing supplying an equal and opposite force of that. It's in an opposite direction. It happens to be equal, but it's not an equal and opposite force to that. Instead, the way that we find it, I can illustrate it here having written it down. I want to swap the subject and direct object. So subject, direct object. And then I want to change the direction and flip that around. The equal and opposite force is Earth is pulled up by the book. With 10 newtons of force. The equal and opposite forces have to have the same source. Yeah.
If you read what your arrows say, it sounds really goofy. How could, you know what I mean? Your sentence just sounds goofy.
Couldn't follow.
Earth was pulled down by the book. Why would Earth be pulled down by a book?
No, it isn't. It's pulled up.
Yeah, I know. I'm just saying in your original sentence.
Oh, but I switched the direction.
I'm just kind of being dumb here.
It's kind of a.
Okay, good one.
Travis got it. Travis laughed.
I did chuckle, but
Okay.
what he was talking about.
Super duper. Okay, let's think about, so off camera here, let's move on. Let's say that I'm pushing my chair around with 20 newtons of force. What's the equal and opposite force of me pushing my chair with 20 newtons to your right?
Your chair is pushing you back.
To the left,
What?
20 newtons. How can that be? I was moving my chair. How can it be applying the same force back to me if I'm clearly pushing it? What about friction?
I don't know.
It rolled.
I just, it seems like a pretty good
The
answer.
kinetic
roll.
friction.
That's not the only force here, right? My force and the chair's force are equal and opposite, but there are other forces at play. Friction is the main culprit here.
Uh-huh.
I have a lot more friction between me and the floor than the chair does and the floor. So my overall force is still that way. And so although I'm applying 20 newtons of force to the chair, it's applying 20 newtons of force back to me. Friction is not fighting me with 20 newtons of force. So the overall object here, the chair, might have 20 newtons that way, only 5 newtons this way. So it accelerates that way. I just wanted to highlight that because we didn't talk about it yesterday. And so since I recorded yesterday,